Hello, friends. Ben again. I am recording a video here for free class. I thought I would try to do it with headphones on, but it doesn't seem to work very well. And so the topic that we're looking at is getting the notions of cylindrical coordinates and then spherical coordinates together. Uh, and this is kind of condensing two things that we were formerly going to put as separate topics into a single day. So hopefully this video won't run very long, but bear with me because I'm kind of long-winded. Also notice that I'm broadcasting from my beautiful back porch where it is just a little bit nippy. So I got my jacket on and everything, but that's some encouragement for me to get finished with this quickly. All right, so polar coordinates and cylindrical coordinates, first off, are the same thing. It annoys me that they refer to them as cylindrical coordinates because they're just polar coordinates with a z added in there. Why do they call it cylindrical coordinates? Because it's really easy to express the equation of a cylinder. Later, we're going to talk about spherical coordinates, where it's really easy to express the equation of a sphere. So in any case, let's see whether I can make my iPad display for us. And it looks like I can. Yay! So polar and cylindrical coordinates. So if you were just saying something about polar coordinates, then the conversion things that you need to think about are right here. That you can set up and express that your x is simply that r, the distance from the origin out to the point you're talking about, times the cosine of the angle theta, and just think about your right triangle there, okay? Same thing for figuring out what the y is. Since it's on the opposite side, then you'd have that your sine theta is y over r. Same as you could say cosine theta is x over r. And then you're just solving for x and y. Now, along those lines, of course, x squared plus y squared, the Pythagorean theorem is going to tell you is going to be r squared. And then you can also say that y over x is equal to the tangent of theta. You may, though, also want to refer back to these here when you're making conversions, right? So when we talk about the conversions between two sets of coordinates, then there's a relatively straightforward process of how to do it. You're just plugging in equations. So if I were to give you that in polar coordinates, I have a point 1 comma pi over 4, then graphically, what you would have to think about is that the pi over 4 is just referring to this angle up here counterclockwise from the positive x-axis. And then that 1 is your distance out. So you can then with that take and do these conversions here of just plugging in, and you know that you've got your x value needs to be 1 times the cosine pi over 4. Cosine of pi over 4 is 1 over root 2. If you like to write root 2 over 2, go ahead. And the y is 1 times the sine of pi over 4, so 1 over root 2. And so you would just list the coordinates like that. Now, if you get a set of coordinates and it gives you that the second entry has a multiple of pi, it is probable that you are talking about polar coordinates, but it's not guaranteed, okay? However, if you have no other context clues, that would be a good way to tackle that. All right, more complicated is if I give you x, y points and ask you to convert that into r theta. So here I just made up a couple numbers real quick. As usual, when I made them up without thinking, it got complicated. But if it says 2, -1, you know that the x and the y are going to be 2 and -1. And that should tell you from your knowledge of algebra that since your y coordinate is negative and your x coordinate is positive, you are down here somewhere in the fourth quadrant. You can either express that with a negative angle that's between 0 and negative 90, or between 270 and 360. Okay. However, we're not going to do stuff in degrees. We're going to do them in radians because that's what we do. Okay. All right. So once we know that it's in the, oh, doofus, I wrote third quadrant. Ah! And then I had the big eraser on. Sorry. I wrote third quadrant and I meant fourth quadrant. Okay. So you can get the R easily enough by just taking the square root of the x squared plus y squared. So we end up with a square root of 5. And then we can say that our sine of theta is going to be equal to the negative 1 divided by the square root of 5. To which you immediately say, whoa, dude, why would you do that? You get a perfectly good y over x for tan theta down here. Well, I just want to make the emphasis here that you could figure out sine theta, you could figure out cosine theta, you could figure out tan theta. You can use any one of those. If you use either sine theta equals negative 1 over root 5 or tan theta, which would be equal to what? Negative 1/2. Either one of those are going to get you stuff that is in the right-hand half of the unit circle. If you use the cosine, you will get stuff in the upper half of the unit circle. If both your x and your y coordinates are negative, then you've got something down there in the third quadrant. The thing to do is to go ahead and get your inverse tangent in that case, which will give you something in the first quadrant, and then just add pi to it, or subtract pi, either way. Okay. So for us, we've got this sine is equal to negative 1 over root 5. That is not a special angle at all. So we are going to just come in here and say that it is the negative of the inverse sine of 1 over root 5, or the inverse sine of negative 1 over root 5, same thing. And the value that we end up getting out of that is about negative 0.4636 something. And usually 3 digits past the decimal will be good enough if you're needing to approximate it. If you don't have to approximate it, just leave it like that. Okay. So the point that I got out of this was square root 5 comma minus inverse sine of 1 over square root 5. And I didn't have to do an approximation there. Okay. So converting points should be easy, but you have to make sure that you realize that when you're converting equations, the answer is not a point. If you're converting points, the answer is not an equation. You just have to figure this out. Okay. If you start with an equation, the final answer should be an equation. If you start with a point, the final answer should be a point. If I sound exhausted when I say that, it's because I've been saying the same thing for 20 years. So, and it's just something that people have a hard time with. So, all right. So this example here, we're going to talk about taking a rectangular equation, x plus y equals 3, and we're going to convert it into a polar equation. Now, x plus y equals 3, you know what that looks like. The graph of that is going to be a straight line. And it's easy enough to figure out the two intercepts of it are going to be 0, 3, and 3, 0. Okay. So if I want to convert that into polar, I just have to remember the conversions for x and y and plug them in there. And now I have r cosine theta and r sine theta added together gets me 3. And what you should do as a last step is to factor that and divide. And then you'll have r equals 3 over cosine theta plus sine theta. You might ask, why do I bother doing that? Well, most of the time when you write equations that are dealing with y and x, you'll have y equals f of x. So most of the time you're dealing with r and theta, you want to talk about r as a function of theta. So really more to the point, if all you do is put one set of equations in and you don't do any algebra or anything, it's a little lazy, you know? So show me that you can do some algebra there, all right? So here is a harder one where we've got r equals 4 sine theta, and we're asked to convert it to rectangular. You will get similar problems that ask you to do this with negative 4 sine theta, or something that might ask you to do this with 2 times the cosine of theta, things like that. They're all basically the same sort of thing, just in different positions. So the trick on this is that if you were to take and multiply both sides of the equation by r, then r squared here is something you know how to convert, and r sine theta is something you know how to convert. So that means that we can trade it in and get x squared plus y squared equals 4y. Not quite finished. We want to put that into a familiar form before we finish with it. So if you put the y's over to the other side, then you have something where you can complete a square and get x squared plus quantity y minus 2 plus quantity squared equals 2 squared. It is the circle of radius 2 centered at the point 0, 2. Okay. Any of those other forms that I said were kind of similar to this will also be circles that happen to go through the origin. Okay. All right. So when we talk about cylindrical coordinates, as I suggested, it'll be super easy to write equations of cylinders. But here's a couple of equations real quick where knowing things in cylindrical coordinates kind of helps you see what's going on. So the equation here, we've got x squared plus y squared minus z squared equals 1. So x squared plus y squared, clearly you're going to replace with an r squared. And so that means that the equation for this in cylindrical coordinates is r squared minus z squared. Now, if you lived in the RZ plane, that is to say, since there's no theta, you could think about any cross section that's going through the z-axis, and then think about this RZ plane here. That figure there, you should recognize, is going to be a hyperbola, and the hyperbola is going to have a horizontal axis. So the axis of symmetry for your hyperbola, the transverse axis, I should say, of the hyperbola is going to be in the direction of r. Now, once you take that and think about rotating it in order to get your thetas in there, you get this sort of shape out of it here. We refer to that sort of shape as a hyperboloid of one sheet. And I guess I ought to just write that down here. Well, it did not want to write. Wow. Hyperboloid of one sheet. If you had done the substitution in here and had z squared minus r squared, then you would have had your hyperbolas going like that instead. And that would have given you a hyperboloid of two sheets, because you would have had something up here and something down here as well. Okay, so seeing hyperboloids in cylindrical coordinates is kind of convenient. Then another thing that's easy to express here is seeing something about the equation r squared plus z squared equals 4. If you again thought about that in the RZ plane, it would be a circle of radius 2 centered at the origin. And so when you rotate that by letting theta be anything that you want, then you're going to get a sphere like this. Insofar as converting it, you're just replacing r squared with x squared plus y squared. And so then you can recognize the sphere of radius 2 from just the standard equation. So, all right. Then a couple of quick sketching sort of problems here. If I ask you to sketch z equals h minus ar, again, this is a problem that doesn't have any thetas showing up in it. And if we looked here and thought about that as being a straight line in the ZR plane, and then we rotate it around the z-axis, the shape that we should get formed in our mind is going to be like this, some kind of a cone. In particular here, since I made the height the h, then you would end up having it hit the z-axis there like that. And then I just put an a times r so that you could make the base of it be whatever you wanted to. Okay. Now, technically speaking, then I could extend these out and think about having my two cones that are intersecting there, something like that. But, you know, just the basic shape is what I was looking for in the sketch here. Here is another one that r equals 2 sine theta. Let's see, we did something on the previous page. Okay, something pretty similar. This is r equals 4 sine theta, okay? So our r equals 2 sine theta, if we went ahead and solved out on that, we would end up getting an x squared plus y minus 1 squared is equal to 1. So in the xz plane, we would look and see something that's a circle that is tangent to the pole, is the phrase we use with polar coordinates. But since now we also have a z coordinate, then you have to think about taking this circle that you got and translating it up and down forever to get all those different cross sections that you could have in it. So that gives you a cylinder out of it. Simpler than that would be if I had just say r equals 3 or something, then I would have a circle which has a radius of 3 centered at the origin, and that would be then another cylinder that you might get for one of these. Okay, so I think that's it for these. Yep, that's right. Now let's switch over here, and I clicked the wrong button. Oh well, there we go. Let's switch over here and talk about spherical coordinates. So spherical coordinates are something that is very much a three-dimensional thing. In a sense, you could think that your cylindrical coordinates or your polar coordinates are a switch from rectangular into something that has to do with an angle. And then spherical is taking that a step further and getting two angles in it. I always like to make the comparison in this that these are kind of how starships would have to give their headings and stuff. If you ever watch Star Trek and hear the captain give some sort of heading like 27 Mark 3-1 or something like that, they would be giving two angles, one angle being off of the forward direction, and then the other angle being to locate where in a circle around that they might be thinking of going. So anyway, it's probably not exactly what they have in mind. I kind of doubt that they really have that sort of thing mapped out as well as we might think. So, all right, so here is a quick sketch that should help us relate a little bit all of the various things going on that we might see in here. So if we're talking about just your cylindrical coordinates here, then you take a point on there. I should probably have labeled my point with an X, Y, Z, but you could also label it with the R theta Z, okay? But your X, Y, Z would then have the X coordinate being the distance away from the Y axis on the XY plane, your Y coordinate being the distance from the X axis on the XY plane, and then your height above the XY plane is going to be given to you by the Z coordinate. And of course, all you have here is your R, which I did not label down here, but because it was going to be in the way, but your R is going to be that distance that you got from that right triangle, right? And theta being the angle that you have to rotate through, but you probably then want to think about the theta being an angle not of two lines, but of two planes, because you got to kind of rotate the positive x-axis, which essentially means the xz plane. You have to rotate that around to a certain position, okay? So our spherical coordinates, what we're going to do now is have rho be the three-dimensional distance from the origin to the point we're thinking about. Now that immediately should tell us that you can do the distance formula and that you can write down, I think, I'm not sure if it's on the next page or if it's on this page. No, it's not there. Okay. You can write down that this rho squared, yes, I know it looks like a P, but it's a Greek letter rho, that your rho squared is going to be x squared plus y squared plus z squared. It's just the distance formula, but without writing the square root in there. Okay. Anyway, though, then, sorry, I have dogs. The theta that you've got, you can talk about it in the exact same way as you did about the theta that you had in cylindrical coordinates. However, the phi that we have is a little bit harder to see on these, and probably the easiest way to put it in here is going to be to take a look at what I've got here for equations and see that I could take, now it's easier to see it there. I could take these two things and do a division. And when I do that, then because I would have a tangent of phi, I would then have to have r over z, or the square root of x squared plus y squared over z. So, and all that stuff got a little bit too scrunched up in there. Okay, so the thing that you really need to think about, though, is that we've got the positive z-axis, and then we've got the angle going out, the line segment going out to our point, and then we want to think about the angle that those two line segments make. That angle is going to be somewhere between 0 and 180 degrees, or 0 and pi radians, okay? Whereas our thetas went all the way from 0 to 2 pi, our phi will always go 0 to pi, okay? People tend to have a hard time remembering that. They also have a hard time remembering it is the angle down from the z-axis, not the angle up from the equator, right? Okay, so with those in mind, let's think about a quick example here. Hilarious, right? A quick example where we're converting from rectangular to spherical coordinates. The other direction, converting from spherical to rectangular, I expect you can just plug into formulas and get it. That's not hard. This, however, is a little bit tricky. First thing is that your rho is just plug in, okay? So I gave you minus 3 root 2, 3 root 2, and 6 root 3. And so to get rho squared, just square all those and add them up. We end up with a 144. So the rho, you know, would either be plus or minus 12. We're going to choose to work with the plus 12. But just like with polar coordinates, you can have negative values, but man, does it complicate things to let that happen. So So we're going to think about it with positive values if we're not told to do something otherwise. Okay. All right, then we're going to get, we're going to try to get our phi figured out here. And the easiest way to do that is to remember that z is given to us by rho cosine phi. And we know that the z is supposed to be 6 root 3. And we know a value for phi, or for rho. So that means that you can solve and get cosine of phi is square root of 3 over 2. And so figuring out your phi, because it's always going to be between 0 and pi, you should always try to use an inverse cosine, not an inverse sine. Okay, use an inverse cosine. And fortunately, that's a special angle, so we end up with pi over 6. Okay. All right. Then we still have to figure out the theta. And the theta is a little bit harder here. We have to look and see that the theta, well, if we were just looking at it x's and y's, we'd say something about this being in quadrant 4 in 2 dimensions. And if we're in quadrant 4, yeah, and I wrote the wrong thing there. That would not be quadrant 4. That would in fact be quadrant 2. So we've got a negative x value and a positive y value. Okay. So with regard to that, then it's probably easiest to go ahead and try to look at things with a cosine of theta. And so we're writing down that our y was negative 3 root 2, and our rho sine phi, we've got a 12 sine phi cosine theta. We know that the sine of pi over 6 is 1/2, so that makes this part into 6, and then when you divide, you'll end up with your cosine theta to be negative root 2 over 2. And then you do an inverse sine and you get 3 pi over 4. And then entering these, it can be a hassle. Check your book and make sure. But I believe that the way that we're supposed to express these is to go rho phi theta. If you reverse the two of them, then it can get things kind of messed up. So go check your textbook just in case I've entered it the wrong way. Go ahead and make sure that you do it the right way. Okay. All right. Then we're going to do a few of these where we're converting equations instead. As I go along here, I like to give us a visual. So x plus 2y plus 3z equals 6. We know that that's a nice linear equation. So the plot that we should get from that, if we go to the computer, is that it should be a plane. We know if we let x and y both be 0, we end up getting the z to be positive 2. If we let x and z to be 0, the y will be positive 3. If we let y and z be 0, then we know that we get the x to be positive 6. So that says that we've got a plane that has to intersect the coordinate axes in those 3 spots there. Once we know that, we can kind of get a visualization of it, right? So for our purposes here, though, we can take and replace x, y, and z with their conversions. And if it didn't ask us to do any more, we could just stop there, but we really ought to try to simplify. Usually it's simplest to try to solve for the rho. So I end up with 6 over a big messy bunch of stuff that you just get from factoring and dividing. Okay. There's not really anything you can do that looks any better with it. Sorry. If you look back to the earlier example where we did, what was it? X plus y was equal to 3, I think. And we solved and got that the r was equal to 3 over sine theta plus cosine theta. You can do a phase angle thing on that one and make it a little bit prettier. But this one here, ugh, this is really as good as you'll get on it. Okay. All right. This one here, we're being asked to convert to spherical coordinates, and we've got x squared plus y squared minus 3z squared equals 0. Okay. The equals 0 here makes this different than the example we had on cylindrical coordinates where we had hyperboloid of one sheet. in a sense, this 0 is a degenerate case of a hyperboloid of one sheet where the neck of it kind of goes down to being 0 width. So anyway, if you just go ahead and substitute here, you end up with a big mess. Rho squared, sine squared, cosine squared, plus rho squared, sine squared, minus 3 rho squared, cosine squared. Blah. But if you notice, you can factor a rho squared out of the whole mess. And this piece here has a common factor of sine squared phi, and then cosine squared plus sine squared is 1. So that's the reason why this turns into sine squared phi minus 3 cosine squared phi. Now, if that is equal to 0, then that says one of the two factors was 0. If you got rho equals 0, that's the sphere of radius 0 centered at the origin. In other words, it's just the single point at the origin. The other option is having this sine squared minus 3 cosine squared equals 0. So if you go ahead and solve for it, that gets you that the tangent of phi is going to be either plus or minus radical 3. Radical 3, tangent theta equal radical 3 is a special angle, and that gets you pi over 3. So if you think about going from the North Pole and down with an angle of 60 degrees, and what you've got there, because theta is not specified, is going to be one of these cones here. If you do negative root 3 instead of positive root 3, then the angle you've got is actually down here at the 2 pi over 3 instead. Okay. So one of the things that you should spot out of this is when we say phi equals an angle, we're going to have a cone which has as its axis either the positive or negative z-axis, depending on where the angle is at. Okay. All right, so then here we've got a problem that asks us to sketch rho equals radical 6. Rho is a distance from the origin. So all the points that are at a distance of radical 6 from the origin would be a sphere. So sketching that should be pretty easy, okay? A little harder to figure out what's meant is if we say theta equals pi over 2, okay? So that means that we need to think about starting with the XZ plane over here and rotating it through an angle of pi over 2. It's like 90 degrees, right? So what we will get then is going to be the positive y part of the YZ plane. Why is it just the positive part? Well, if you got the negative y values there, that would be over on this other side, then that angle would be either negative pi over 2 or positive 3 pi over 2. You know, either way that you go at it. But that would just be a different sort of display for it, okay? All right. So I'm going to go ahead and leave that at that. You've got a lot of problems to try this sort of stuff out on. They're not hard. It's just that they take some doing, you know. So go ahead and get in on those and ask me questions about it in class, or ask Don questions about it in class, and we'll talk to you later on. All right.